look at acid-base properties of ions and salts. And when we say salt, we just mean ionic compound. Some ions can act as bases because they are conjugate bases of weak acids. So we saw HCO3- in that list of weak bases. When it acts as a base, accepting a hydrogen ion, it becomes H2CO3 carbonic acid, which is a weak acid. H2CO3 and HCO3- are conjugate acid-base pair. Everybody see that? So what's important to understand here is the acid and the base are just passing a hydrogen ion back and forth, right? The acid is the adult, the parent, the base is the babysitter. So the adult passes the hydrogen off to the base, but now the base has the baby, right? Has the hydrogen ion, and so it could pass it back. So whoever has the hydrogen ion is the acid, and the other part is the base. And they just go back and forth, okay? So here, in this reaction, this guy gained a hydrogen. It accepted the hydrogen, so this is the base, and that's the acid. Okay? Everybody okay with that? If we have an ion like this, it has to have a counter ion in the solution. You can't have a jar of chloride ions. You can't separate charges like that. So this is going to have to be something like sodium hydrogen carbonate or potassium hydrogen carbonate, because it can't come in as a negative ion. It has to be part of a neutral compound. So soluble salts, soluble ionic compounds, dissociate in solution, and we're going to pretend they dissociate completely. So sodium hydrogen carbonate is going to form sodium ions and hydrogen carbonate ions. And what are the sodium ions going to do? Nothing. They're just like, la, 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 I'm in the solution. The HCO3- can act as a base. It can take hydrogen ions from a water molecule and form hydroxide. The sodium's not going to do anything like that. So this is part of why we made you learn about net ionic equations in Chem 1A. Because there are a lot of times, especially in this class, where we're only looking at one of the ions. But the other ion is there. If we were going to make a solution that was like 1 molar in HCO3-, we would have to weigh out an amount of sodium hydrogen carbonate to get 1 mole. So we'd have to use the molar mass of this. We can't just ignore that it's there. And so when you see something like this, in your supply list in lab, and then you're doing something with hydrogen carbonate ion, you're like, well, what happened to this? Well, the sodium is just hanging around. It's not doing anything, okay? So if we have a solution of sodium hydrogen carbonate or sodium bicarbonate, it's going to be basic. Baking soda is basic. And so on each bench, we have a shaker of sodium bicarbonate, baking soda. And yesterday I got to use that twice to clean up acid spills. You can use it to neutralize acids. Any questions yet? So we could think of any anion as being the conjugate base of an acid. If you have a conjugate base, in order to make the acid, you put a hydrogen ion on it. So here, A-, if we add a hydrogen ion to that, we get HA. This is the acid. That's the conjugate base. Here's a specific example, nitrate ion. Well, you put a hydrogen on that, you get HNO3. That's an acid. This is the acid. This is the conjugate base. Okay? Not every anion will act as a base. It depends on how strong its conjugate acid is. So the conjugate base of a weak acid is a weak base. The conjugate base of a strong acid is pH neutral, doesn't do anything. The weaker the acid, the stronger the conjugate base. So I thought of this yesterday, and I think I like it. So you can think about our acid and the conjugate base. And between them, they have a certain amount of strength. If this one is weak, then it's not using all the strength, and then this is also weak. This is a strong acid, though. This is a strong acid. It's got all the strength, and so its conjugate base has no strength. It doesn't act as a base. Does that make sense? The stronger this is, the weaker that is. If this is weaker, that's stronger. Everybody okay with that? So when we have a strong acid, the conjugate base does not act as a base. So we say it's pH neutral. Chloride ion. Okay, that's an anion. And what's its conjugate acid? Add an H plus to it. HCl. Well, what kind of an acid is that? It's a strong acid. So the strong acid's got all of the strength, and so the chloride, does it act as a base? No, it doesn't. Another way to think about this, HCl is going to completely separate into hydrogen and chloride. That's the definition of a strong acid, right? We use a single arrow. Do you see a path backwards for the chloride to make the HCl? No, it's a one-way ticket. It's done. Here's the weak acid. It ionizes partially. So it's going to make H3O plus or H plus and fluoride ion, but it's not all going to do that. We have the equilibrium arrow, and this is, you can go either way. So if we put fluoride here, it can react with the hydronium ion and reform HF because this is a weak acid. So these guys are both weak acid, weak base. This is a strong acid. This does not act as a base. Any questions about that? It can be a bit confusing. This illustration has a bunch of acids on the left and a bunch of bases on the right, and you'll see that these are anions. These are the conjugate bases of those acids. Up here, HCl is a strong acid, so its conjugate base is neutral. HSO4 minus is a weak acid, so the base SO42 minus is a weak base, but it's way at the weak end. And so as these get weaker and weaker, their conjugate bases get stronger and stronger. Okay? So it's like this plus this, that's the total amount of strength they have. And with these guys, the HCl has all of it, and the Cl minus has none of it. The weak acids in here share more, and so this one has some strength, and that one has some strength, but the more strength this one has, the less strength that one has. It's a fixed amount. I'll work on that analogy. I'm sure it can become better. Okay, classify each anion as a weak base or pH neutral. What we want to do is look at the conjugate base of this anion. So how do we make a conjugate, did I say conjugate base? I'm sorry, conjugate acid. We want to look at the conjugate acid of this anion. So to make the conjugate acid, we add H plus, right? So that would give us HCHO2. I put the hydrogen on the front because hydrogen is a positive ion, and this is a negative ion. And so that's how we usually write things, the positive and then the negative. And that may or may not look like an acid to you, but it does start with H. Is it a strong acid? No, it's not one that's on the list. Therefore, it's a weak acid. So this is a weak acid. What does that make the anion? You can only have strong and nothing, or weak and weak. It's going to be weak. It's going to be a weak base. Yeah, I need to flesh out that analogy. How about this one? What's the conjugate acid of that? Slap an H plus on it. HCl O4. Strong or weak acid? Strong, because it's in the list of 6. If this is a strong acid, does this act as a base? No, it can't. This one is so strong, it's not going to let that one do anything. This one is an acid, but it's weak, and so this one is also going to be able to act as a base. So this is considered pH neutral. It's not going to change the pH. Any questions? So we can figure out the pH of a solution containing an anion that acts as a weak base, but we need to know what Kb is. So an anion acting as a base is the conjugate base of an acid. So here's the acid. The acid reacts with water to form hydronium ion plus A minus. That's our anion that acts as a weak base, because the anion can react with water to form hydroxide and HA. You see where those two equations are coming from? This is the acid doing its thing with water. This is the anion, which is the conjugate base, acting as a base with water. Okay? So we could write if I chose a pen. So this is the ionization for the acid, right? And this is a reaction for the base. So we could say that the equilibrium constant for this guy is going to be Ka. Again, water, liquid, doesn't show up. And here we have a base doing its thing. So the equilibrium constant for that one would be hydroxide times HA divided by A minus. Everybody okay with that? Let's see what happens if we multiply Ka times Kb. is going to be H3O plus times A minus over HA times hydroxide HA over A minus. Some things are going to cancel out, right? A minus is going to cancel out, HA is going to cancel out. And so what we get is hydronium ion concentration times hydroxide ion concentration, and that had a special name, Kw. That's the ion product constant for water. And it equals something, 1 times 10 to the minus 14. Yeah, so Kw is 1 times 10 to the minus 14. And this is the equation for the autoionization of water, right? The equilibrium constant for that is this times this, Kw. Well, I really don't know how that happened. Kw. So Ka times Kb equals Kw. That's the relationship. You don't have to know how to get there. So if we're looking at an anion from an acid, we're probably going to be given the Ka value, but we need the Kb value. So this is how we're going to find what Kb is. Ka times Kb is going to equal 10 to the minus 14. So find the pH of a 0.25 molar NaC2H3O2 solution. Ka equals 1.5 times 10 to the minus 5. This is an ionic compound, right? Metal, non-metal. We learned in Chem 1A that we separate those into 2 ions, 1 cation, 1 anion. I hope you recognize that as acetate, but if you don't, it's okay. The metal is all by itself. Everything else is the anion. Okay, so we've got this anion. Is the sodium going to do anything? No, it was just there as a counter ion. What is this the conjugate base of? What is its related acid? Acetic acid, HC2H3O2, which is a weak acid, right? So this is a conjugate acid-base pair. So this guy is going to act as a base. So we're going to write a chemical equation showing how that acts as a base. It's going to react with water. The base takes a hydrogen ion. The babysitter accepts the child, HC2H3O2. So here, the water was acting as an acid. It handed off the hydrogen, handed off the baby, and then what's left of it, what's the concentration of acetate ion? 0.250. That's the concentration of sodium acetate, but these guys separate, right? So 0.250. We don't care about water. What about the HC2H3O2? That's going to be 0. And the hydroxide? Essentially 0. Okay? And then we're gonna put x's in there. These have to be plus, because from 0 you can only go up, and that will be minus. Are you okay with that? We've like done it a bajillion times now. The next thing is write the equilibrium expression, right? This is a base, so it's KB, and it's equal to the products divided by the reactants. So we have the equilibrium concentrations for those guys in terms of x. So we could plug those in. We're going to have x times x on the top, which is x squared, and 0.250 minus x on the bottom. But they told us what Ka was. This is Kb. So Kb is going to equal Kw divided by Ka. 1 times 10 to the minus 14 divided by Ka. Yeah, I did it wrong. Yeah. So yeah, 5.556 times 10 to the minus 10. Kb times Ka equals 1 times 10 to the minus 14. So now we have a numerical value for this guy. And so this is our equation that we're going to solve for x. Again, I'm going to use the solver. Doesn't matter which side you put on the left in the equation, it's going to come out the same. I got 1.17 times 10 to the minus 5. Anybody else get that? Somebody has to check my work because I make an awful lot of mistakes. Okay. What does x represent? It's the change, but it's also the equilibrium concentration of this guy and that guy. This is the equilibrium concentration of hydroxide ion. They're asking us for the pH, not the pOH. So again, we're getting on the circle of pH and we're taking a half spin. So pOH is the negative log of the x that we just found. 4.9285. pH then is 14 minus that. If you do 14 minus this number, because you zoomed into the screen too far, the answer doesn't make any sense. Okay, let's try that again. I'm subtracting 4.9285. Okay, that's much better. 9, yeah, writing with the eraser. 9.0715. 9.07. Thank you. And that's what the book got, too. It's always nice when we get the same answer.
It's wonderful.
Yeah. What's really frustrating, and I think I fixed them all, there were some, the answers to these are in the textbook, in the back. But some of them, the answers are wrong. And so we would do one in class, and it's like, what did we do wrong? And we finally just had the book's wrong. That shouldn't happen. Not on the 6th edition? What?
This has been peer reviewed by so many people at this point. How did everybody come to that same conclusion?
Well, I think a lot of people realized it was wrong and just didn't bother to say anything. And then,
And
people
then
like me who do say something, they don't listen. So, any questions about this one? Which anion acts as a weak base? I think I heard A, B, and C. Well, what are we looking for? We need to look at what kind of an acid did this come from? So this came from HCl. This came from HBr. This one came from HF. Yeah? If this is strong, that's nothing. This is strong, that's nothing. This is a weak acid, that's also a weak base. Questions like this can show up on exams, and they can kind of just like surprise you because you spent so much time learning how to do ice tables that you're like, oh wait, there's no numbers, what do I do? Any questions? Okay, so those were the anions. Now we have to talk about cations. Cations can sometimes act as weak acids. So anions can act as weak bases. Cations can act as weak acids. They can, sometimes. So there's 3 different categories. We can look at counter ions of strong bases. The base is strong, so the conjugate is going to be nothing. It's so weak, it's nothing. We've got strong and nothing, or weak and weak. So these are going to be pH neutral. Strong bases dissociate completely. Their counter ions do not ionize water. So examples would be calcium, sodium, and potassium. So, potassium hydroxide. This is a one-way thing. It just separates into ions, and that potassium's not going to do anything. So, like the conjugate base of a strong acid does not act as a base. Here, cations that are counter ions of strong bases do not act as acids. Okay? And then we have some that are conjugate acids of weak bases, and these can act as acids. So a cation that's the conjugate acid of a weak base is a weak acid. So here's our weak base. When this acts as a base, it's going to pick up a hydrogen ion and make this cation. That's a weak base. This is going to act as a weak acid. Any questions? The pH, we can calculate using Ka that we have to derive from Kb. I think we did an example of that one. So when we were talking about the anions that were conjugates of weak acids act as weak bases. Here, we're talking about cations. If they're conjugates of weak bases, they can act as weak acids. So if one conjugate is weak, the other conjugate is also weak. If one is strong, the other one is nothing. Okay? So I think the most important thing is weak base, weak acid. If one's a weak base, the conjugate is a weak acid. If one's a weak acid, the conjugate is a weak base. And how would you recognize that? Well, what if you had NH4+? You're like, well, I know that's the conjugate of ammonia, but is it going to act as an acid or a base? Well, if it was going to act as an acid, it would give off a hydrogen ion, right? If it was going to act as a base, it would have to gain a hydrogen ion. Hopefully this looks really weird. NH52+ doesn't exist. Okay, so look at the conjugate. This is a weak base. That means this is a weak acid. So they just matched up like that. Yes? What, the NH3? No, it doesn't. The NH3 doesn't have a negative because this had a positive. So when we took one positive away, we're left with neutral. Yeah. Okay. And there's one more group. Sorry. These are small, highly charged metal ions. The two that you need to know are Al3+ and Fe3+. So these can act as acids. How does this happen? The ion becomes hydrated. So we've got this ion in water, and the water molecules are going to come around and put their negative side towards the ion, and they're going to hang out there. So now it's got 6 water molecules around it. One of these water molecules could lose a hydrogen. So this is acting as an acid. And so you get funky formulas and equations like that. And that also looks ridiculous, but is it actually a real thing? So if you see Al3+ or Fe3+, those can be acids. I'm not sure why, but this is Al and that's Iron Man. So Al and Iron Man, small, highly charged, act as acids. Okay. Classify each cation as a weak acid or pH neutral. So lithium. And we could say, well, what's lithium the conjugate of? What happens if we put an H plus on it or take? We can't do that. There's no H plus to take away. Well, what base would it be related to? LiOH. That's a strong base. This is the cation from a strong base, so this is nothing. pH neutral. How about this one? CH3NH3+. Well, could we take a hydrogen off of that? Yeah, we could. So this is acting as an acid. This is the base. Is that a weak base or a strong base? It's a weak base, because strong bases look like this, LiOH, NaOH. They've got OH in them. This doesn't. So this then acts as a weak acid. Are you okay with that? Fe3+. It acts as an acid. Because I told you it did. And I told you to remember it. And that's a good enough reason for now. Okay, so what if we have a salt solution where we have cations and anions? And we've got a possibility for the cation to be a base and for the anion to be an acid. That's backwards. Yeah. The cation could be an acid and I don't know. One can be one and one can be the other. Yeah. So and the pH of a salt solution depends on the specific cation and anion involved. And so what we do is we look at each of them and see what they are. So we practice doing that with cations and with anions. So we can have a salt where neither of those acts as an acid or base. So this is going to be pH neutral. In this situation, the cation is going to be the counterion of a strong base, like lithium or something like that. The anion is the conjugate base of a strong acid. So these are examples. Let's just look at this guy. What ions does that form in solution? Calcium plus and NO3 minus. Yeah, it does make two of those. Is this the counterion of a strong base? That would be put OHs on it. Yeah, that could be a thing, right? And then this, what's the related acid to that? HNO3. And this is a strong acid. This is a strong acid, so that's nothing. This is the counterion of a strong base, so that's nothing. So you put these in this water, it doesn't change the pH at all. We could have salts where the cation does not act as an acid and the anion acts as a base. So then we're going to have a basic solution. Here we're going to have a cation being the counterion of a strong base, and the anion is the conjugate base of a weak acid. So, I think it's actually a little more confusing when we talk about the combinations here. What you'll need to be able to do is if I give you something like KNO2, is that solution going to be acidic or basic or pH neutral? And so what we're gonna do, let's do this one. We're gonna look at the separate ions. So we've got K plus and NO2 minus. Is this related to a strong base? Yes, it is, KOH. Is this related to an acid? What acid is it? HNO2. What kind of an acid is that? It's a weak one. NO3 is strong, but this one's weak. So if this is a weak acid, that means this guy acts as a weak base. So I think general strategy is just take the two ions apart and look at each of them separately. Here's one where the cation acts as an acid, the anion does not act as a base. Let's look at this guy. Take the ions apart. This is a salt, but it doesn't have a metal in it. NH4 plus is the cation. And that was the one polyatomic cation you were supposed to learn in Chem 1A. All the other things, it's going to be a metal and something else. But NH4 plus is the cation. And then what's left is Br minus. So just watch out for that, because that can, you're looking at things like this and then you're like, wait a minute, is that ionic? Yeah, it is. Okay, so NH4 plus, what's that related to? NH3. It's not the cation of a strong base, right? So this is a weak base. So what's this? Weak acid. Br minus, what's it related to? HBr. Strong acid, weak acid? Strong acid. So the Br then, nothing, neutral. So here we've got something being a weak acid and something doing nothing. We're going to have an acidic solution. And then you can have possibilities where the cation acts as an acid and the anion acts as a base. And so they're going to kind of fight against each other. The only thing you can do there is to compare the Ka and the Kb, and the bigger one wins. I'm not going to give you questions like that on an exam. This is a table summarizing that information, which you may or may not find useful. And this is the sort of thing we should be able to do. Okay? Each solution, is it acidic, basic, or neutral? What are the ions? Remember, 2 ions in NaHCO3. The first one's a metal, right? Na is a metal. So that's going to be by itself, and then everything else is going to be the anion. Every time. What kind of a base is this related to? A strong base, NaOH. So is this going to do anything? No. What kind of an acid is this related to? A weak acid. Put an H on there and we get H2CO3. Weak acid. That means this is a weak base. And this one's nothing. So the solution will be basic. This one kind of looks like a mess. I would not expect you to say, oh, that's an ionic compound. Because it isn't really. Can we make two ions out of it? Yeah, we can. We've got this NH in here, which should remind us of ammonia, right? So the NH and its cha-chas are going to be together. And then what's on the end? It's Cl minus. So CH3, CH2, NH3, and Cl minus. We know that Cl minus is a negative because of its position in the periodic table. What does that make the charge on this guy? Positive 1. Is this related to a weak base? We've got an N. Yeah, so if we take a hydrogen off of that, hydrogen ion, we get that. This is a nitrogen with hydrogens and carbons, therefore it is a weak base. If this is a weak base, then that's a weak acid. What about Cl minus? It's the conjugate base of a strong acid, HCl. So that one's going to do nothing. So is this solution going to be acidic, basic, or neutral? Acidic. Because one of the things acts as an acid. KNO3. Okay, this is a nicer ionic compound, right? We've got K plus and we've got NO3 minus. Is K plus related to a strong base or a weak base? Strong one, KOH, right? So that's not going to do anything. And NO3 minus is related to a strong acid. So this is going to be so weak that it can't do anything. So that one's going to be pH neutral. And then our last one here, FeNO3,3. So we got Fe there, and we've got NO3 minus. There's 3 of them, it doesn't really matter. Does this act as an acid? It does, because that's Iron Man. Iron Man and Al, they act as acids. So this acts as a weak acid, because I told you to remember that it does. This is related to what kind of an acid? A strong one. HNO3, that's strong, so that one's nothing. So we've got a weak acid, and that's all, so this is going to be acidic. There's not really any memorizing that I think would be super useful there. If you understand it, you can figure it out. But you have to understand it. And so if you need help understanding it, please hit me up, okay?